Hello mathematicians. In this video I am going to work through the pre-calculus chapter 3 practice test. So as always, feel free to fast forward to whatever problem you need. So this first one has this function that's given, f of x, and it's going to be used to answer number 1 through 4. Number 1 just says what is the lead coefficient. So the lead coefficient is just the number in front of the term actually with the highest power. So this one is actually a little tricky. As you notice, it almost got me there. The lead coefficient is actually going to be this -3, because if we rewrote this function in standard form, the -3x to the 5th would be first, then plus 2x cubed, then plus 12x, and then plus 32. So remember, your lead coefficient is always in front of the highest term, and that would be -3. The number of zeros is your degree. It tells you the number of solutions. So in this case, that highest power of 5 would be the number of zeros. The constant term is the number without an x, so in this case, positive 32. And then lastly, I know this is kind of a strange variable to use, but it's just saying if you know that negative beta is a 0, that means x plus beta would have to be a factor of that polynomial. Just like if we said 7 would be a 0, we would put x minus 7. If we said -2 would be a 0, we'd put x minus -2, which would be x plus 2. So that's just asking, or trying to get the idea of what a 0 means versus what a factor means. All right, in this next section, we're going to use this p of x function. The first thing they want us to find are the x-intercepts. So remember, x-intercepts are just what make each factor equal 0. So we have x equals 1, x equals -3, and x equals 3. So when you write those, you should also write down what their multiplicities are. So that x equals 1 solution has a multiplicity of 3. That x equals -3 solution has a multiplicity of 2. And the x equals 3 just has a multiplicity of 1. So when we start looking at number 6, in number 6 we're going to actually graph a sketch of this, or sorry, in number 8. So just remember, like, this multiplicity of 3, since it's odd, means that the function is going to cross there. Since this multiplicity is even, it's going to bounce there. And since this multiplicity again is odd, we know we're going to cross at that 0. Okay, to find your y-intercepts, you just plug in 0 for x. So you just let x equal 0. So we're going to say y equals 1 minus 0 cubed times 0 plus 3 squared times 0 minus 3. So that ends up being 1 cubed times 3 squared times -3, which just ends up being -27 if you simplify that correctly. All right, so let's look at what we have so far. I'm going to put a point 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. And then since this is just a basic sketch, I'm just going to say that this way down here is my -27. I'm going to say this here is 1, 2, 3, 4, 5, -1, -2, -3. So I'm going to put what we have so far. I have my zeros, which are at 1, -3, and 3. And I'll put my x-intercept of -27. So if we look at the end behaviors, overall, if you FOILed out this entire polynomial, you have a -x cubed, and then this would be like a x squared for this this middle term, and then this would end up being an x. So if you took negative x cubed times the x squared term in the middle times the x term at the end, that would have a power of 1. So overall, you would get a negative x to the 6, which tells me that this is going to be a negative, and since it's even powers, it's going to be a parabola. So the basic shape of a negative parabola is just a parabola that goes down. So on both sides, your y would approach negative infinity, like on the left side of this graph, as your x's are approaching negative infinity. So like we're looking at this left side. And y would also approach negative infinity as x approaches positive infinity. So that's just saying on the right side of the graph, it's also going down. So if we look at number 8 now, we can put all of that information together and we can say, okay, I know I need to cross at this negative, or bounce at this -3 solution, and I'm starting from negative infinity. We bounce here, come back down, cross this y-intercept, go up and again cross here, and then come back down. So if you're looking at that and saying, well, that's not very beautiful, like, it's okay. I just want to see that I bounced here at -3, I crossed at 1, I crossed at 3, and my end behaviors are both going down on each side. And then lastly, I'm checking that, okay, my y-intercept of -27 is being graphed. So a sketch just means, like, do you have those basic things? Later, we'll look at graphing more accurately. All right, so the next part is using Descartes' rule of signs, determine the nature of the roots of p of x. Complete the table showing all possibilities. So the first thing we're going to look at is the number of positive real roots, which, if we remember, in the notes we called those positive real zeros, or the PRZs. So if we look at the signs of each term, we have a negative, a positive, a negative, and a positive. So since that changes signs 1, 2, 3 times, that tells you could have 3, or you walk it down by a 2, or 1 positive real zeros. The second thing you do to figure out your negative real roots, or your negative real zeros, we called those in the notes, was to replace x with negative x in your function. So we'd have negative x to the 5th plus 5 negative x cubed plus 9 negative x squared minus 28 times negative x plus 6. So I don't really care what those end up being. I just know that this first term would be a negative times a negative would be positive. Positive 5 times a negative x cubed would be negative. Negative x squared is positive, and then times a negative 9 is positive. Negative 28 times negative x is positive, and then that 6 is positive. So now if you look, we change signs 1, 2 times. So we could have 2, or if you walk it down, 0, negative real zeros. So you just keep going down by 2 until you get to either 1 or 0. All right, so let's look at our table here. If I have 3 positives and then 2 negatives, that's already giving me 5 total real roots, which is the degree of this function, which means I don't have room for any imaginaries. Okay, well now let's suppose I have 3 positive real zeros and no negative real zeros. Well, then I have only 3 real roots, which means I have to have 2 imaginary roots to get this total degree of 5. All right, and then the last thing I could look at, well, what if I only have one positive real root? And then I could have two negative real roots, which only gives me, again, 3 real roots, which means I would have to have 2 imaginaries in that case as well. And then our last combination is, again, I could have 1 positive real root, 0 negative real roots, which only leaves me with 1 real root, which would mean 4 of my roots or zeros have to be imaginary. So if you add these 2 columns, the real roots and the imaginary roots, those should always equal the degree. And one thing about your imaginary roots, remember those always come in pairs. So this number should always be even. Your real roots can be anything, but the imaginary roots have to be even. All right. So now we're going to look at some division here. In number 10, we're going to use synthetic division. And if you're going to use synthetic division on this problem, remember your C value is whatever makes the denominator equal 0. So if you were going to solve that, this would be -1/2. So when I set this up, -1/2 is going to be the number that I have in the corner. And then I have 6, -7, -3, and -6 as my coefficients. I didn't have to put a placeholder in because it goes from power of 3, power of 2, power of 1, and then the constant. So if we bring down that 6, -1/2 times 6 is -3. -7 plus -3 is -10. -1/2 times -10 is 5. -3 plus 5 is 2. -1/2 times 2 is -1. And then we get a remainder of -7. Now don't just leave this as your answer. If it says use synthetic division to divide, you should figure out that this is your remainder, constant, coefficient of x, and coefficient of x squared. So my final answer should be 6x squared minus 10x plus 2. And then that is -7 over what you were dividing by, which is 2x plus 1. All right. So if we look at actually, this is your final answer for number 10. All right, let's look at 11. So now we're taking this p of x function, or we're saying p of x is this polynomial divided by x minus 5. So when I refer to q of x, we're going to assume that that's the quotient, which, like if you look at this previous problem, this would be the quotient or q of x. And then r of x we're going to call the remainder. So in this problem, that would be the -7 over 2x plus 1. So number 10 didn't ask you for that, but that's kind of where we're going with number 11 here. So this is a good candidate for synthetic division. So I'm going to use 5 as my c value. And then my coefficients are 2x to the 4th, -7x cubed, -10x squared, and then notice they skipped the x, so I'm going to have to put a 0x as a placeholder. And then I have my constant. So I bring down my 2. 5 times 2 is 10. -7 plus 10 is 3. 5 times 3 is 15. -10 plus 15 is 5. 5 times 5 is 25. 0 plus 25 is 25. And then 5 times 25 is 125, which gives us a remainder of 124. So again, remember this is your remainder, constant, x, x squared, x cubed. So the quotient is going to be 2x cubed plus 3x squared plus 5x plus 25. So I'm going to call that q of x just to fit the problem. then we're going to write our remainder separately. So that's just based on this part. Your remainder is going to be positive 124 over what we were dividing by, which is x minus 5. All right. And then the last one is just saying, okay, what if you wanted to find p of 5? Well, p of 5 would just be 124. That's the remainder theorem. The remainder theorem says whatever you get for this remainder is the same thing as if you were just going to plug in 5 to that equation. So instead of having to do 2 times 5 to the 4th and all that, you can just say that the answer is 124. All right. Number 12 switches gears a little bit here. So in number 12, we are going to find the possible rational solutions. So in the notes, we called that the P over Q thing. So this is P, and then this is Q. And you just put the factors of the constant, which we called P, over the factors of the leading coefficient. And you divide all of those out to get your possible rational solutions. So in the notes, you'll see that as P over Q. So if we look at the constant, that's 8. So the factors of 8 are positive, negative 1, 2, 4, and 8. The factors of Q, which is just 5, are positive and negative 1 and 5. So if we divide all of those out, 1 divided by 1 gives you 1. 2 divided by 1 is 2. 4 divided by 1 is 4. 8 divided by 1 is 8. Now we divide everything by 5. 1 divided by 5 is 1/5. 2 divided by 5 is 2/5. 4 divided by 5 is 4/5. And 8 divided by 5 is 8/5. So put a plus minus in front so you know it's positive and negative, and those are all your possible rational solutions of f of x. All right, in this next section, we're going to be working with i's. So this was section 3.4. The first thing is actually pretty simple. This is just combining like terms. Just be careful that you distribute that negative. So this becomes 7 plus 2i plus 1 plus 6i. And then your like terms are the 7 plus 1 is 8. And positive 2i plus 6i is plus 8i. And you can just leave your answer like that. All right. In 14, we need to FOIL. So we're going to take 5 times 3, which is 15. 5 times negative 2i is negative 10i. Negative 4i times 3 is negative 12i. And then you have negative 4i times negative 2i, which is plus 8i squared. So remember, you should never leave I squareds in your answer. This term back here is actually 8 times negative 1. So remember, I squared is always negative 1. That is something you should not forget. That's going to come up a lot in these last few problems. All right, so if we simplify this, we have 15 minus 22i, and then it's positive 8 times negative 1, so it's minus 8. And if we combine the 15 minus 8, we get our answer, which is 7 minus 22i. All right, number 15. The issue with this one is that you have i's in the denominator. So to get rid of those, we can FOIL this out by the conjugate, which is 5 plus 2i. So on the top, you will have to FOIL. So if we FOIL 2 plus I with 5 plus 2i, we are going to end up with 10 plus 4i plus 5i and then plus 2i squared. And the bottom, whenever you are foiling a conjugate, you can just do the first and the last, because notice your plus 10i and your minus 10i will cancel, so you don't have to do the outsides and insides. So 5 times 5 gives you 25. And then negative 2i times positive 2i is minus 4i squared. And then again, remember, this piece and this piece both become negative 1. So our next step is going to say 10 plus 9i, and then it's going to be 2 times negative 1 here, which is minus 2, all over 25 minus 4 times negative 1. All right, so our last couple steps are just simplifying. 10 minus 2 is 8 plus 9i, and then 25 minus 4 times negative 1, well, that's going to be 25 plus 4, which is 29. So there's really nothing you can divide 8, 9, and 29 by, so then this would be our answer. All right, 16, we had a problem kind of like this on the 3.4 assignment. So what I would start with is writing this as I squared to the power of, if I put 61, that would give me I to the 122nd, and then I'd have this lonely I left over. Now the reason I chose I squared to some power is because I know I squared is negative 1. So this turns into negative 1 to the power of 61 times I. And any power of a negative 1 to an odd power, this is just going to end up being negative 1 times I. And negative 1 times I is negative I. So we're just trying to break up this into something I squared to some power. Kind of the rule of thumb, if this exponent is odd, your answer is going to be negative I. If the exponent would be even, like say I had I to the power of 48, for example, well, that you could write as I squared to the 24th, which is negative 1 to the 24th, which is just going to be 1. So if that was an even power, 1 is always going to be your answer. All right, so this was just a little extra example for you. All right, 17 is one that we're going to have to do quite a bit of work. This one says find all zeros of the function f of x. So we're going to combine first, starting to find our list of possibles. So that's our step 1. P in this case is negative 4. Q is 1. So my factors of P would be plus minus 1, 2, 4. Those are the factors of 4. And the factors of 1 are just plus and minus 1. So my list is just 1, 2, 4. Positive, negative. So the second step is now I just have to keep doing synthetic division until I get a remainder of 0. So I always just start with 1. And I usually do this second step starting with a pen. And actually I should have left some space so I can put my possible in the corner. So I have 1x cubed, negative 4x squared, 6x, and negative 4. All right, now I'm going to switch back to pencil and I'm going to try 1. So I bring down the 1. And you know what? If you want to, that part you can also do with a pen. So that's not going to change. So 1 times 1 is 1. Negative 4 plus 1 is negative 3. 1 times negative 3 is negative 3. 6 minus 3 is 3. 1 times 3 is 3. And I get a remainder of negative 1. So what that tells me is positive 1 doesn't work. Let's erase this. And now let's try negative 1. So we bring down the 1. Negative 1 times 1 is negative 1. Then you get negative 5. Negative 1 times negative 5 is positive 5. That's 11. Negative 1 times 11 is negative 11. And I get a remainder of negative 15, which is not 0. 0 is the magic number we're trying to find. So hey, guess what? Positive 1, negative 1 doesn't work. All right, let's erase that. And let's try 2. All right, so positive 2. Let's see if this gives us something. 1 times 2 is 2. Negative 4 plus 2 is negative 2. 2 times negative 2 is negative 4. 6 minus 4 is 2. And 2 times 2 is 4. Negative 4 plus 4 is 0. So we found it. So here's what I'm left with. Remainder, constant, x squared. So I have x squared minus 2x plus 2. And at this point, for step 3, you have 2 options. You are trying to solve x squared minus 2x plus 2 equals 0. Option 1 is it's factorable. Well, can you think of 2 numbers that multiply to negative 2 and add it to 2? No, you can't. It's not factorable. So if it's not factorable, which in this case it's not, you have to use the quadratic formula. All right, so that's going to be our last step. You have I'm not going to sing for you guys, although I know you would really love that. So the opposite, let's see, this is your A, this is your B, this is your C. So we have the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. So that's if you plug in correctly. So these are going to give you what the other 2 solutions are. All right, so we have 2 plus or minus. And then up above, I usually show like the work on this. This is 4 minus 4 times 1 times 2 is 8. So that's just going to be square root of negative 4. And then it's all over 2. So we have 2 plus or minus the square root of negative 4 is 2i divided by 2. And since you can divide those out, 2 divided by 2 is 1, plus or minus 2i divided by 2 is I. So I always like to, at the end, just make a box with all of my solutions. Notice that on this problem, I have a power of 3. That's the degree. So I should have 3 solutions. I do. Remember, this 2 is a solution because it gave us a remainder of 0. Then we have x equals 1 plus I, and we have x equals 1 minus I. So those are our 3 solutions to this polynomial. All right, 18 says write the standard form equation of the 3rd degree polynomial with these zeros. And you might be looking at that and saying, well, that's only 2 zeros. But remember, imaginary zeros always come in pairs. So the pair to this would be negative 3 plus 2i. So they always come in conjugate pairs, which means that your factors are, if you have a 0 of 0, that would be like x minus 0, which is just equal x. So I'll have an x in front. I'll have x minus negative 3 minus 2i. And then I'll have x minus negative 3 plus 2i. Okay, and I'm just going to call this polynomial p of x. So that's the easy part. The hard part is now just simplifying. So this is going to equal x times x. If I distribute that negative, I get plus 3 plus 2i. And then again here, I get x plus 3 minus 2i. So you'll always want to FOIL the part with i's first. So x times x is x squared. And we get plus 3x. And then we get minus 2ix. And if we distribute this 3, we get plus 3x plus 9. And then 3 times negative 2i is minus 6i. All right, the last thing to distribute is the 2i. So we get plus 2ix. And then 3 times 2i is plus 6i. And then 2i times negative 2i is minus 4i squared. And then that whole thing is still going to be times x. Now, if you do this right, all the pieces with i's should cancel. This minus 2ix, this plus 2ix. This minus 6i, this plus 6i. And then this last term turns into negative 4 times negative 1, because I squared is always equal to negative 1. So that's going to end up just being a plus 4. So if we combine like terms, we have this x out front. Then we have x squared. 3x plus 3x is plus 6x. 9 plus 4 is plus 13. All right. And then last step is to distribute that x. So p of x is going to equal x times x squared is x cubed plus 6x squared plus 13x. And that would be your polynomial with those zeros. All right. 19 wants us to find the complete factorization of this function. And they give us a little hint here. So we're actually going to need to start this kind of like we did in number 17. Or, yeah, just like number 17. Okay, so first thing I would do is find my possible rational zeros. So that's the p over q stuff. So in this case, p is negative 20 and q is 1. So 20 does have a lot of factors. So if you put your p's over q's, it's going to be plus or minus 1, 2, 4, 5, 10, and 20. Luckily, q is just 1. So when we divide those out, we get just plus or minus the factors of 20, which there are quite a few. But this hint right here is helpful. This tells me that x equals negative 4 is a 0. So when I start my synthetic division in step 2, I'm going to start with negative 4 because I know that's going to give me a remainder of 0. So now I put my coefficients of this polynomial, which are 1, 7, 9, negative 17, and negative 20. All right, so if I do my synthetic division, I will get this leftover polynomial here. And let's see. Oh, this should be a negative 5. So negative 4 times negative 5 is 20, and I get my remainder of 0. So at this point, I would try using negative 4 again, because it turns out that sometimes that factor might be like to a power of 2. So I'm going to use this 1, 3, negative 3, and negative 5 as my new polynomial. So this is going to make things a little bit easier. And I'm going to try negative 4 again. Maybe that'll work. So I bring down my 1. Negative 4 times 1 is negative 4. 3 times plus negative 4 is negative 1. Negative 4 times negative 1 is 4. Negative 3 plus 4 is 1. And I no, that does not work. So -4 only is a factor once. So at this point, I'm going to say, okay, let's go to the beginning of our list, and now I'm going to try +1. So if I try 1, I'll still bring down that 1, and I get this. And if I use 1, I get a remainder of -4. So +1 didn't work. Let's try making it a -1 and reworking this process. So if we try -1, we end up bringing down the 1. -1 times 1 is -1. 3 minus 1 is 2. -1 times 2 is -2. -3 minus 2 is -5. -1 times -5 is +5. -5 plus 5 is 0. All right. So I found my quadratic. This is your remainder constant x squared. Once you get this down to an x squared function, you're always going to end by solving that quadratic. So that's your last step. As I take this x squared plus 2x minus 5, and I set it equal to 0. So again, you could try factoring it, but -5 and 2 is not factorable. So you have to use quadratic formula. So our x's are going to equal the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times 1. So if you simplify that down, you get -2 plus or minus. This is 4 plus 20. So that's going to give you 24 for the root part. And then that's all over 2. And then you can break up root 24 into root 4 times root 6, which then that is just 2 root 6. So we could get -2 plus or minus 2 root 6 all over 2. And then you can reduce that down. -2 divided by 2 is -1. 2 divided by 2 just gives you plus or minus 1 root 6. So we found all of our zeros, okay? Now we have to go back and put them into our factors. So if you want a list of your zeros, well, -4 gave us a 0, -1 gave us a 0, and then these are our other two. So we'd have x equals -4, x equals -1, x equals -1 plus root 6, and x equals -1 minus root 6. So if we write our complete factorization, it's going to be p of x equals x plus 4, which we already knew was a factor, that was given, x plus 1, and then x plus 1 plus root 6, and x plus 1 minus root 6. So this is our polynomial completely factored using those zeros that we came up with. All right, in 20, we're asked about the degrees of a rational function. And we are given that f of x is p of x over q of x. And they say if y equals 0 is a horizontal asymptote, compare the degrees of p and q. So I'm going to write this out as if y equals 0 is a horizontal asymptote, then the degree of the numerator's function, which they're calling as p, is less than the degree of the numerator's function, which they are calling q. And in our notes, we called this like the degree of the numerator was greater than not greater than. The degree of the numerator is less than the degree of the denominator. So that was like that table that we filled out in the notes. 21 says if there's a slant asymptote, compare the degrees of P and Q. So if there is a slant asymptote, then the degree of the numerator's function, which they're calling as P, is exactly one more than the degree of the denominator, which is Q. All right. So in 22, it says use transformations of the rational function y equals 1 over x to sketch the given function. So you have to think back to like shifting the parent functions. And in general, the graph of 1 over x always has asymptotes at x equals 0 and y equals 0. So it's like this would be the graph of 1 over x. That's the parent graph. So thinking of shifts, this plus 3 is going to move everything left 3. This minus 1 is going to move everything down 1. So by everything, the easiest way to do this is to start with that parent graph and then just move your asymptotes. So the x equals 0 vertical asymptote that we usually have here is going to move left 1, 2, 3 and be at x equals -3. So this is the line x equals -3. The horizontal asymptote, which is normally at y equals 0 for this parent function, is going to shift down 1. So then it's going to be, this is the line y equals -1, which is your new horizontal asymptote. So these branches are still going to like hug the vertical asymptote and that horizontal asymptote. But then that center point, if you look at this point right here, is now at -3, -1, where it was before at 0, 0. And that is because of those shifts. All right. And then the last two are actually going to be looking at graphing accurately. So we're going to have to find all of this information that you see listed down below. All right, 23, the first thing that I'm going to do is just start factoring. So actually we can just do this by starting to find things. So your vertical asymptote is usually what we found first if you look in your notes. And remember, you can get a vertical asymptote where the denominator is equal to 0. So all you have to do is set your denominator equal to 0. And I would actually do this by just factoring. I would say this is a difference of squares. So I have x plus 2 times x minus 2, which gives me x equals -2 and x equals 2. So those are your vertical asymptotes. And I'm going to put those on the graph right away. So I have this -2 vertical asymptote, and then I have this x equals 2. All right, that's all I've got so far. All right, your horizontal asymptote is what I'm going to do next, is based on the degrees, and I know that I do have a horizontal asymptote because the degree of the numerator is equal to the degree of the denominator. So if that's the case, if you look in your notes when they're equal, because this is a 2 and a 2, you get a ratio of the lead or the leading coefficients. So in this case, my lead coefficient at the top is 2, and my lead coefficient at the bottom is 1. So y is going to equal 2 over 1, or we just get y equals 2. So that is your horizontal asymptote, y equals 2. All right, so you can start to see what's kind of going to happen here. Now, you can't have both a horizontal asymptote and a slant asymptote, so you need to know that if the degrees are equal, you have this happening, which means you don't have a slant asymptote. All right. Next thing we're going to find are the x-intercepts, and remember you get x-intercepts when the denominator is equal to 0. Or sorry, where the numerator is equal to 0. So I'm just going to write myself a note that this happens where the numerator equals 0. So I can factor the numerator, so I take a 2 out first. Then I'm left with 2 times x squared minus 9 equals 0. And that, again, is a difference of squares, x plus 3, x minus 3. So I get x equals negative 3 and x equals 3. So if I wrote my x-intercepts as ordered pairs, I'd have negative 3, 0, and 3, 0. So on my x-axis, I have a point here and a point here. All right, and then the last thing, your y-intercepts, just plug in 0 for x. So 0 is going to equal 2 times 0 squared minus 18 all over 0 squared minus 4, which is just negative 18 divided by negative 4, which is positive 4.5. So your y-intercept is 0, 4.5, which is 1, 2, 3, 4, right about there. So now the last thing I need to do is just to see, like, I know what's happening on the left and the right of this graph because you can't cross the horizontal asymptote at the ends. So I know I have this branch on the far left, and I know I have a branch that looks pretty much the same but reflected on the right. So I have to figure out what's happening in the middle. So I'm going to make a little table. I already know that if I plug in 0, I get 4.5. But what if I plug in negative 1? Well, then I get positive 5.3 if you do all that work. So at negative 1 for x, I get 5.3 for y, which is about there. If I plug positive 1 in, you'll also get 5.3 when you do that math, which tells me it goes up on this side. So in the middle here, you end up with this kind of parabola looking thing going on. So it's really the middle where like something unexpected can happen. The far left and far right branches should just be approaching your vertical asymptotes and your horizontal asymptotes. All right, so this here is our final graph. All right, 24 is our final problem. And we're going to go about this pretty much the same way we did number 23. I'm going to start with my vertical asymptotes, which again, those occur where the denominator equals 0. So for this one, it's just going to be x minus 1 is equal to 0. So you can see if you solve that, you get x equals 1. So if I graph the vertical line x equals 1, I know where my vertical asymptote is. All right, the next thing I'm going to find is my horizontal asymptote. But I notice for this one that the degree of the numerator is greater than the degree of the denominator, which means I don't have a horizontal asymptote. I do, however, have that this is exactly 1 more than this, which means I have a slant asymptote. And to find that, you have to use a little bit of synthetic division. So I'm going to put 1 in the corner because that would make the denominator equal 0. And then I have 1x cubed minus 1x minus 2. So when I do this little synthetic division, I end up with, this is my remainder, my constant, and my x. So y is going to equal 1x plus 0. So you don't really care about the remainder when you're doing this process. So the line y equals 1x plus 0 is where you're going to have this slanting asymptote. So it's going to go through 0, 0, then it's going to go up 1 over 1. That's just the line y equals x. I know I'm putting a lot of dots, but I want to make sure I graph this accurately. Okay, so we have an idea of where this graph is going to live. If we find our x-intercepts, then we'll know where to finish. All right, so my x-intercepts, remember you set the numerator equal to 0. So do those. So it's where the numerator equals 0. And that can be factored. So if you factor x squared minus x minus 2 equals 0, that's just x plus 1 and x minus 2 equals 0. So I get x equals negative 1 and x equals 2. So negative 1 comma 0 and 2 comma 0 are my x-intercepts, which if I graph, negative 1, 0 is here, and then 2, 0 is right here. All right, the last thing I need to graph is the y-intercept, which you find those by just plugging in 0 for your x's. So y-intercept, we're just going to say y equals 0 squared minus 0 minus 2 all over 0 minus 1, which is negative 2 divided by negative 1. So that's just going to give you 2. So 0 comma 2 is your y-intercept, which is right here. And I would maybe just plug in one more point so you can see like what's happening. So if you make just a super tiny table, I'm just going to plug 2 into this function just to get a better idea. If you plug 2 in for x, or sorry, not 2, we know there's a vertical asymptote, or we know there's an x-intercept at 2. So I'm going to plug in 3. If you plug 3 in, you get 2 for y, which means if I go over 3 up to, I have a point here. So this just gives me a better idea of what's happening. My final graph is going to look like this. It's going to have this branch getting closer and closer to that slant asymptote, and then it's going to start to go like straight up to that vertical asymptote at x equals positive 2, or sorry, x equals positive 1. And then you're going to have this other branch in this region, which again is going to get closer and closer to that diagonal slant asymptote, and then start going straight down at that vertical asymptote. All right, so that's kind of the basic shape there. Did I really need to do this? Probably not. I could have probably gotten away without it. But if you're ever unsure of where the graph is living, you can make as many values of a table as you want to get a better idea of what it looks like. All right, so let me know if you have any questions. Feel free to comment down below if you can't see me in class. All right, take care.